Let's develop an equation for vibrato using what I'll call the intuitive approach. And to begin with, let's consider a sinusoid at a constant amplitude A and a constant frequency f0. And you've perhaps encountered this equation many times in the past. If we consider the spectrogram, that is the frequency versus time plot, since this is a constant frequency at f0, its spectrogram would look like a single line that continues at that same position as time goes on. Well, if we think about our goal for vibrato, we would like to have the frequency kind of shift around a little bit around this nominal value of f0. So, as I say, this is kind of the intuitive approach. If we think of f0 as being the term that controls frequency, then it seems reasonable to say that, well, if f0 is a constant, then what we really need to use is a time-varying frequency. So I'll call this f0 of t. And according to our spectrogram picture, it looks like we would like to have a sinusoidal variation about the constant frequency f0. So let me write the sinusoidal variation as delta f times sine of 2 pi fr of t. So delta f is my frequency deviation, fr would be my rate, which would be a rather low frequency compared to f0. The sine itself is centered about 0, so I need to lift that up to the position f0 by adding a constant. I have a lot of f0s going on right now, so just to perhaps avoid confusion, let me call this just a generic time-varying frequency f of t. So it seems that we can then take our original sinusoid, and where we had f0, let's drop in our time-varying frequency function. We still have the t multiplier up on top, and that completes our equation for vibrato. Well, let's check this out, listen to it, and see how well this actually works. I have a LabVIEW VI set up that implements that exact equation we were looking at. I have controls for delta f, which would be depth, and I'm calling it FM for modulation frequency, but that's our rate. FC controls my tone frequency, and I'm plotting the time-varying function and looking at the audio. Well, it sounds kind of interesting, but it doesn't really sound like somebody's singing with vibrato. Now, if you listen carefully, you should hear that the frequency deviation appears to be getting more or greater with time. Let's try a smaller starting value. If you listen carefully, you can hear how the frequency deviation keeps increasing. Let's try that one more time. A nice special effect for a science fiction movie, perhaps, but not very satisfactory for vibrato. So, why doesn't this work? Well, what we need to do is consider the total phase function associated with our sinusoidal argument. And maybe it'll be a little bit easier if we start with the original phase function for a constant frequency sinusoid. And I will plot that phase function phi of t as a function of time. The 2, the pi, and the f0 are all constants. Therefore, this describes a constant ramp with slope 2 pi f0. So to get a little intuition on this phase function, if we were to increase its slope, we have a higher frequency. If we decrease its slope, we have a lower frequency. But in all cases where we have a constant frequency, we have this constant ramp. So a ramp gives us the shape for a phase function that translates into a constant frequency. Well, let's return to the phase function that we perhaps inadvertently designed here. Here we have the notion of a sinusoid centered about f0. But the big problem here is we are still multiplying this function by a ramp, t. 2 pi t if you like. But essentially we're multiplying a ramp times that sinusoidal undulation. That's why we see the frequency deviation increasing without limit as time goes on. So it would appear that the depth continually increases with time, and we really need the depth to stay constant with time.